Assalamu alaikum. So in today's video I would be going through the LAMMPS script which we would be using for running our simulations. So here is a basic simulation. So in this simulation you would be seeing that there is a material and we are pulling the material from both ends, and what happens is a crack is formed, and this would be our study, that where the crack is forming and how the crack is propagating. So all this can be done with the help of molecular dynamics simulations which we would be running in our LAMMPS. So here are the basics of LAMMPS code setup. So if you see that these are mainly the commands category. So firstly there is initialization. So in initialization there are different things, like there is Newton, there is package, processors, which indicates the number of processors and the units we would be using. The second is setup simulation box. So the main simulation is run within a box, and this setup simulation box is the part where we define which one is our box or how our box is formed. So this includes boundary, dimensions, lattice, region, etc. The next part is setup of atoms. So here we would be setting up our atoms and what type of properties they would be carrying. Moreover, if we want to define groups, the mass, the molecules, all this can be done within this command. Next is the force field. So in this force field we would be mainly discussing the force that is acting between the atoms. So the commands that are present here are angle coefficient, angle style, bond coefficient, bond style, pair modifier, pair style, etc. Then we find settings. In the settings mainly we deal with the neighbors, the neighbor modify, the different time step, etc. Next we would be talking about operations. So this is where our main simulation runs. So here we would be talking about if we want to fix the simulation or if we want to compute it, and we would be also talking about the time steps. Then we would be talking about our output. So mainly after the simulation is run, in this part we would be talking about how and where our output is stored. Then we would be talking about which format our output is saved into. For example, if you want to dump into an image, or if you want to dump in the form of a movie or a form of a textile. Moreover, we can also say what kind of outputs we require, like do we need temperature, do we need the energy, etc. Then there is actions and input script control, which we would not be using as much. Like in actions we normally use the minimize, and in input script control mainly we can clear all our simulations or all our results up to a certain point. So if you open the LAMMPS installation folder, there is a folder named examples. If you go into that folder, there are different kinds of examples present. We would be working with crack. So if you go into that folder, you would be finding a file named in.crack.lmp. So in this file, this is mainly the LAMMPS input script code, and we would be discussing this code. So you see here I have opened this. So if you want, I want to divide this into several parts. The first part, this is mainly the creation of our input simulation box. The second part, the geometry, so how our material is designed, what kind of atoms are present, this should be defined in the second step. In the third step, we find the LJ potentials. So we would be defining what kind of force field is acting between the atoms. Then we can define the groups. So this one is for our better understanding. By defining the groups, we can clearly understand where the crack is forming, which groups we are keeping fixed, and where we are applying the force. Then we can set our initial velocities, which in some cases indicate the temperature. Here we are fixing some of our boundaries. Then in this time step we are mainly running our simulation for a particular time period. This is our neighbor modify, and finally this indicates our dumping or output. So this indicates where we are saving our output. In today's video I would be talking about this part only, that is the creation of the initial simulation box. Okay, so here if you look at this part, this particular part, we have dimension, we have boundary, we have atom style atomic, next we have neighbor 0.3 bin, and then neighbor modify delay 5. So firstly we go into dimension. In LAMMPS the default setting is that there would be 3 dimensions and we would be running our simulations in 3D. But if you want to run a 2D simulation, you have to explicitly define that dimension 2, that is you are working with 2 dimensions. Next you find boundary. So what does boundary mean? For example, you have a box. Let this be your simulation box. So in this simulation box, you see these are your boundaries. This will indicate how your material, how your atoms within the simulation box will act when they come outside of this boundary, how they will act in such cases. So if I want to elaborate it, for example, let this be your simulation box. You have an atom, you have 4 atoms here. So your atoms are displacing in this direction. Your atoms are displacing. So after one time period or after one time step, what will happen? The first atoms will come into this position and the second group of atoms will come into this position. So what will happen in such cases, or how will your boundaries, these are your boundaries, how will your boundaries react to such kind of changes? So this kind of things will be discussed by the boundary conditions. So there are 4 kinds of boundary conditions: P, F, S, M. P indicates periodic. These 3 are non-periodic, where F means fixed, S means shrink wrapped, and M means shrink wrapped plus mirror. So if I go individually to each of the boundary types, firstly we find periodic. So what does periodic mean? So for example, you have 4 atoms here. The atoms are displacing along this direction. So after a while, what happens is, in the next time step, let your atoms be in this condition. So what the periodic boundary condition does is, it throws these 2 atoms again within the simulation box. So in the next time step you also have 4 atoms. So you might think that this kind of looks unrealistic, but the thing is, when we are working with a large material and there are infinite number of atoms or molecules here, and we are only working with a particular simulation box here. So when our simulation box is moving, or when the for example, let our simulation box be moving, and from here the simulation box is going here. So even if the simulation box is moving, the number of atoms here and the number of atoms here is not changing. So in such kind of cases we use the periodic boundary condition. So let's go to the other types of boundary condition. For example, you have the shrink wrapped, you have the fixed. So what does the fixed do? So for example, let this be your simulation box and the atoms here. So if the atoms go in this direction, the second atoms come here. So in the next time step you have 2 atoms here, 2 atoms here. What the fixed boundary condition does is, it completely eliminates these 2 atoms. So in the next time step, when you would be running the simulation, you would be running the simulation with only 2 atoms in the second time step instead of the 4 atoms in the first time step. So you might say, in which cases are this applicable? For example, when you are running the simulation in case of the surface of a material, for example, the simulation box is this one. So, and you are running the simulation along this direction. In such cases, when the atoms go outside of the simulation box, it is very realistic that the atoms will not return to the simulation box. So in such cases, fixed boundary condition may be the way to go. Then you find shrink wrapped and shrink wrapped plus with a minimum value. So what this does is, for example, this is your simulation box with 4 atoms here, and after some time these atoms come here. Let the atoms be like this place. Okay, so what the shrink wrap does is it extends its boundary, or it might also decrease its boundary in some cases. So what it does is it shrinks or wraps its boundary so that it can accumulate all the atoms present in the simulation. In the previous time step, it retains that. The difference between S and M, that is shrink wrapped and shrink wrapped with a minimum value, is that in case of a minimum value, there is a limit to how much it can shrink or how much it can wrap. So if it goes with the after or beyond a certain value, then it cannot wrap the atoms further. So this is the main difference between shrink wrapped and shrink wrapped with a minimum value. If you look here again, you will see that after boundary there are 3 different letters. Firstly, periodic, periodic, fixed. So why do I need to write it 3 times? The first one is x-axis, the second one is y-axis, and the third one is z-axis. If you look at the second line, you would find that in the second box you see F and S. So why are there 2 letters here? So in some cases you can use the double letter. The double letter means that the first letter indicates the lower face while the second letter indicates the upper face. So for example, this is your simulation box and you are saying that along the x-axis it is fixed and shrink wrapped, which means that this portion, if this one is your lower, then this one would be the fixed and this one would be your shrink wrapped. So you can see that Fs and Fm, so these 3 can act 2 at a time, but periodic acts only 1 at a time. That means when you are saying that along some axis your boundary conditions are periodic, it cannot be periodic plus shrink wrapped or periodic plus anything. Why is that? You need to understand that if this is your simulation box and the atoms go out through this direction and again come back in this direction, you need to apply periodic to both this direction and this direction. So when you are applying periodic along an axis, you cannot add a second letter indicating that it is periodic in one phase and another property in another phase. It cannot be simulated in that way. If you are defining periodic along a certain direction, it would be periodic in that direction in both phases. I hope I could make myself clear. Then you can find the atom style. So what does atom style mean? Atom style indicates the atom style command selects which per atom attributes are associated with atoms in a LAMMPS simulation and thus stored and communicated with those atoms, as well as read from and stored in data and registered files. But it means that when you are running a simulation, the atomic properties can be stored and different kind of properties can be stored. So you know that atoms hold different kind of properties, like they may hold charge, they may hold forces, velocities, positions, etc. So the atom style atomic indicates a subset of per atom attributes. For example, there is tag. This tag indicates atom type or ID. This type indicates which type of atom you are using. X indicates the position, V indicates the velocity, F indicates the forces, and there is image and mask. So all these can be found within atomic. and there are other atomic styles as well. For example, amoeba, angle, body, bond, sphere, charge, dielectric, etc. There are a lot of atomic per atom attributes which you can find in the LAMMPS manual. So I would not be going through all of them today, perhaps in some future video. Next you can find neighbor. So what is this neighbor meaning? What does this neighbor mean? For example, let this be your simulation box and you have all these atoms here. So if I consider the central atom, you see all these surrounding atoms can be considered its neighbors. So up to which range can we consider a particular atom the neighbor of another atom? So in this case, you need to understand some terms. The first term that you need to understand is neighbor cutoff distance. Neighbor cutoff distance. So what is this? It determines the maximum distance within which atoms are considered neighbors and potentially interact. So for example, this is an atom, and up to this distance it considers the atoms which are within this distance its neighbors. So like let all these atoms be within this distance, and this distance we can call it the neighbor atomic distance, the neighbor cutoff distance. But we would be using the skin distance in our code. What is the skin distance? So apart from the neighbor cutoff distance, we use an additional buffer which would be helping with our potential movement. So for example, this atom would be moving a certain distance. It might move a certain distance, so there is a buffer included and our neighbor list might be changed. So what it does is it increases the range. For example, it takes the range up to this. So what it helps in the simulation is we can get a more accurate representation of the number of neighbors for this particular atom, and this is with the help of skin distance. Okay, so the next thing you need to understand is the building algorithm. So if you look at our code, you find the first one is neighbor, the second word is skin, which indicates the skin distance, and next you find style. So what does style mean? Style means that the way in which you would be building your neighbor list. So there are three ways of building your neighbor list. The first one is bin, the second one is NSQ, and the third one is multi. So I would be going through each one of them individually. Let this be your simulation box, and there are a lot of atoms here. So if you try to calculate the neighbor of each of the atoms here, it would take a lot of time, which is computationally inefficient. So what bin does is it creates a certain bins, like let there bins be bins like this. So what it does is, now you can, for example, you want to find the neighbors of this particular bin. What you would be doing is you would be calculating with the neighboring bins and the atoms within this bin. So it helps reduce the computational time while maintaining a very good level of accuracy, and the computational cost of bin scales linearly with the term n by p, where n means the number of atoms and p means per processor. So it scales linearly with this. So if we go into the second one, that is NSQ. NSQ means nearest neighbor squared. So let this be your simulation box. In this simulation box you have like less number of atoms. So in this system, what you would be doing is, for example, we want to calculate the number of neighbors for this one. So you calculate the distance of each and every atom from this particular atom, and by doing this you would be finding which ones are our neighbors. So this is a more accurate approach, but you need to understand that it is computationally very inefficient, so it can only be done in case of very small systems, and the computational cost in these cases is n by p whole square. So you can see that the computational cost increases very much with a small change in number of atoms. Next we find the multi-algorithm. So what does the multi-algorithm mean? For example, you have a simulation system where your atoms are in this system. So if you go through the regular binning system, you will find that, for example, we are constructing bins in this way. So you see that this kind of bin construction is very inefficient. Why is it? Because in the first bin there are a lot of atoms, but in the last bin also there are a lot of atoms. But if you consider a bin here, there are no atoms. If you consider a bin here, there is only one atom. So this kind of binning process does not give you the accurate representation of the number of neighbors. So in such cases, what you do or what we do is use the multi-binning approach. So in this case, our bins are not of regular shape. The shape of our bins varies. So we would be taking a bin, and this is another bin, and this is another bin. So if by varying the shape of the bins, we are going through a more computationally efficient and accurate approach. Next is neighbor modify. This command sets parameters that affect the building and use of pairwise neighbor lists. Depending on what pair interactions and other commands are defined, a simulation may require one or more neighbor lists. So what it does is, let this be your simulation box, and the atoms, like these are your atoms. For example, this atom goes through here, and what happens is the neighbor list might change. For example, in this case the neighbor list was this, and in the second case the neighbor list might become this. So your neighbor list cannot be the same throughout the whole simulation. So you might need to modify your neighbor list after a particular time, or in some cases of a rigid material you might not need to modify at all. So if you need to modify, you can use this particular code. For example, in our LAMMPS code we have used neighbor modify, neighbor underscore modify delay 5. This 5 indicates the time steps. So here you see we have used delay. Instead of delay, you can use different kinds of option. You have every, you have delay, you have check, and you have once. So what does this particular options indicate? The delay and every mainly indicates that after a particular amount of time has passed, you can modify your neighbor list. So in this case, after 5 time steps, you are modifying your neighbor list. What does once mean? Once mean that you are modifying your you are modifying the neighbor list at the beginning of the simulation, and you are not modifying it again. What does this check mean? So this check means that if our neighbor list really needs to be modified. For example, in this case, if the whole simulation box moves from this direction to this direction, you might not need to modify your neighbor list. So what check does is the check option checks if the neighbor list needs to be modified, and if it needs to be modified, then it will modify the neighbor list, and if it doesn't, it will not modify the neighbor list. And in this way you can use the neighbor modify delay, and you can use any number of neighbor modify, you can use any option, you can use any number of time step. If you set a smaller time step, it will modify more and more, and it will happen is you can get a slightly accurate but huge but it will come with a large computational cost. And if you set a larger time step, you can get computationally very cheap simulation, but you might lose accuracy. So you need to find the correct trade-off between the computational cost and accuracy. So this is all for today's video. Thank you.